Uh, I'm from a place called the Joint Quantum Institute, and quantum is our middle name. So I want to also acknowledge the fact that I'm part of the laser cooling and trapping group. Gretchen Campbell is my group leader, and all these other people are names that you've heard of in the quantum business, but they don't have anything to do with what I'm going to be talking about today. I'm going to be talking about the quantum reform of the metric system, and one of the questions you might ask is uh, how quantum is this? Sort of the kind of question that Jose Unuchik was answering. And what I'm going to tell you is that almost all of the quantum features of the International System of Units are 20th century quantum mechanics. Some of the reforms are quite different, so that fits into our theme. And some of the future reforms that we're going to see are going to incorporate 21st century quantum mechanics. That is the second quantum revolution. So the International System of Units is what we call the modern metric system. This system of 7 base units. The physicists are most familiar with kilograms, meters, seconds, and amperes. Um, and the reform that I'm going to be telling you about is that each one of these units is now defined by defining one of the constants of nature. Now, how that happens, I'm going to explain in a very brief a section that I call, with apologies to the late great Stephen Hawking, a brief history of time, because the second has been defined in this way for some time. The original definition of the second was as a fraction of the mean solar day. But as you can see in the bad video, since about 1900, we have known that the length of the day changes, not just during the year, but things like the tides are slowing down the rotation of the Earth. And so it was clear by 1900 that we needed something else that was more stable than the Earth itself. Well, the answer to that was atomic time. It wasn't until the 1960s that the second was redefined as being a certain number of cycles of the radiation that connects the two hyperfine levels in cesium. But the key thing here is that we have replaced something that is a classical object, the rotation of the Earth, with something that is a quantum feature, the energy level difference between two energy levels in the cesium atom. And the way in which this is realized is satisfyingly quantum. The Ramsey method involves superposition of states, and as all of you know, if I create a superposition of the two hyperfine states, then essentially the atom ticks at the hyperfine frequency, and we compare it to our local oscillator, and that's how we realize the definition of the second. And amazing technological developments that make chip size atomic clocks of the sort of thing that one might even carry in a watch are now becoming part of our modern technology. And here's a picture of a laser-cooled atomic cesium clock that has an accuracy of a few parts in 10 to the 16. It's the most accurately realized unit of the International System of Units. So again, what we've done is we've gone from an object, a classical object, to a quantum concept. Now let's talk about length. The original definition of the meter that it was 1/10 millionth of the distance between the equator and the pole. And the way this was measured was they sent people out to survey the distance between Barcelona and Dunkirk. And they came back with the result of what the meter was in terms of the old measurement system. But it was hard to do. It took them years to do that surveying. And so they stored the result in a 1 meter long rod called the meter of the archives. And this became the standard of length for France. And some decades later, the International Conference, the Convention of the Meter, established a new meter bar in which the distance between two scratches enshrined the distance that was in the meter of the archives. But late 19th century France was a hotbed of optics. The idea that light was a wave was fully embraced, and people like Michelson were doing interferometric measurements of length. And in fact, Michelson was the first one to measure the distance between those two scratches on the meter bar using an optical interferometer. And people started to measure lengths in terms of the wavelength of light, a kind of a de facto embracing of a new definition that had not yet happened. It took until 1960, interestingly, the year that the laser was invented, it took until 1960 before they changed the definition. And at that time, the definition of the meter became the wavelength of light from a krypton lamp. But it wasn't long before lasers were producing light that was much purer than the light from a krypton lamp, and people started using laser light as their de facto standard of length, not SI meters, not meters in the International System of Units, but an unofficial length standard, which obviously meant that there needed to be a new definition of length. The obvious choice would have been to redefine the meter in terms of the wavelength of a particular laser stabilized to a particular molecular resonance. Fortunately, they did not do the obvious thing. They did something that was both beautiful and amazing. They defined the speed of light. The new definition of the meter is that it is the length traveled by light in a certain fraction of a second. And the denominator of that fraction is the newly defined speed of light. The beauty of this is that if you take any light and measure its frequency, because we've now defined the speed of light, the wavelength of that light, whatever it is known exactly. So that means that if in the future people make better lasers, and they did, or people develop better ways of measuring the frequency of light, and they did, and here are the people who did that. Jan Hall and Ted Hensch got the Nobel Prize for doing exactly that. Those improvements already were incorporated into that new definition of the meter. So you see what happened was we went from a classical object to a quantum object to something even more fundamental, the speed of light. This is still a quantum definition because we need quantum mechanics to understand our definition of time, but the beauty of it is we should never need to change it again. Now, the new part. We want to bring this beauty, this brilliance of a definition involving a constant of nature, a fundamental constant of nature. We want to bring this to the kilogram, and for that matter, to the ampere, the Kelvin, and the mole. Why? Well, at the French Revolution, they also defined a new unit of mass as well as a new unit of length. The unit of mass was the mass of 1 liter of water, and a liter of water was defined as a cube 1/10 of a meter on each side. This was wonderful because water is universal and the meter is now well defined. But the trouble is that it wasn't very easy to get exactly 1 liter of water, and it wasn't very easy to determine its mass because its density isn't very high and it's quite buoyant in air. And so guess what they did? They made a classical object. There I am holding it. Can you imagine holding in your hand the kilogram of the archives? I did it. I was so thrilled. In 1799, they deposited a platinum cylinder that was as close as they could make it to the mass of a liter of water, and that became the standard of mass for France. And then decades later, at the time of the International Treaty of the Meter, they made another, this time platinum iridium cylinder, and that became the kilogram for the entire world, the last artifact. This is the definition up until 2019 of the kilogram, that it is equal to the mass of the international prototype of the kilogram. Now think about this. In the 21st century, the unit of mass is an artifact made in the 19th century based on an object made in the 18th century. If someone were to leave a fingerprint on that object, all of us would lose weight.
That's very true.
This is scandalous. Well, nobody leaves a fingerprint on the international prototype of the kilogram, but it's obvious that it is changing nevertheless. Now, what has happened to my stopwatch, which I had on here to make sure that I didn't exceed the limit, which Carl is going to keep me very close. You know, he used to be my boss, and now he's acting like my boss again. This is a chart of the mass of a bunch of kilograms that were made at the same time and presumably identical to the international prototype of the kilogram. And you can see that they're all changing by many micrograms. And they're almost all changing in the same direction. This gives you the feeling that maybe it's the international prototype of the kilogram that is changing in the opposite direction, but it cannot, because legally, the international prototype of the kilogram is always 1 kilogram. This, as I said, is scandalous. How do we fix this scandalous situation? We want to do it the same way we did with length. That is, we want to define a constant. So what constant will we define? So in order to understand that, I remind you of the most famous equation in all of history. E equals mc squared means that the energy of an object at rest is equal to its mass times the square of the speed of light. Now, an equation not quite as famous, but one you all know, is that the energy of a photon is Planck's constant times its frequency. We combine these two equations and solve for m. We find that mass is equal to Planck's constant times the frequency divided by the square of the speed of light. What is the meaning of that equation? It means if I have an object like an atomic nucleus that emits one photon, a gamma ray, and I can measure the frequency of that photon, and we know how to do that in principle. I know the speed of light because we defined it earlier in 1983. If I now define Planck's constant, I know what the change of mass is in that nucleus. Essentially, I can weigh the photon, and that gives me a standard of mass. Now, that's not what we're going to do. We can do it, but not nearly well enough. But we're going to use this concept that Planck's constant can give us a new measure of mass to give us a new kilogram. And here is how it works. Imagine that I have an atom at rest, rubidium, let's say, because we love to laser cool rubidium. And I send in a laser with a well-defined frequency that I can measure using the techniques of Hall and Hensch. And that means I know its energy, and more importantly, I know its momentum, which is Planck's constant divided by the wavelength. So when the atom absorbs that photon, it will start moving with a velocity that's simply given by momentum conservation. That velocity is given by Planck's constant divided by the mass and the wavelength. I solve for the mass and find that the mass of the atom is equal to Planck's constant divided by the velocity and the wavelength. The wavelength was easy to measure because I measured the frequency. The velocity is measured by atom interferometry, which many of you know about, but I'm not going to take the time to talk about it. So what it means is I now know what the mass of a rubidium atom is in kilograms, not in funny units like atomic mass units. I know what it is in kilograms, and I can use the standard techniques of atomic mass comparisons to compare that mass of rubidium to the mass of something like silicon. And then I can make a silicon sphere, the most spherical object that has ever been made on the face of this earth. The degree to which this varies from being perfectly spherical is on the order of nanometers. And then you measure the lattice constant in this perfect crystal of isotopically pure silicon. You measure its dimensions, and you have essentially counted how many atoms are in that sphere of silicon. You multiply that by the mass of a silicon atom in kilograms, and you have the mass of that object that can, in this case, is very close to a kilogram. Now, it turns out that's not the only way to do it, but I wish I had time to tell you about another beautiful way of doing it, because I actually spent some of my career doing it, but we don't have time to do that. But the point I want to make is that both of these methods were used, and when they all agreed, the world got together and decided that they would adopt this new definition of a kilogram.
It took more than 140 years.
Groundbreaking science. And the agreement from the world scientific community.
You hear that?
At times, it seemed
Impartial.
accurate.
Precise measurements.
Anytime.
Anywhere. But we did it.
Ce l'abbiamo fatta.
Well, enough of that. The fact that 60 countries of the world, from everywhere, got together and, in spite of their differences and their perspectives about this, unanimously agreed to change the definition of the kilogram, I think is a marvelous example of how we ought to be doing things in our relationships between nations. Well, there's just a little bit more of the story. Where am I? How much time? 5 minutes. Beautiful. The ampere, it used to be that the ampere was that current which between, when put in two long straight wires, would produce a certain force per unit length of those wires. Today, the definition of the ampere is by defining what the charge of a single electron is. So an ampere is now a certain number of electrons per second. If you've defined E and if you've defined H, then that means you've defined 2E over H and H over E squared. 2E over H, according to Brian Josephson, gives us voltage in terms of frequency, and H over E squared, according to von Klitzing, who, shouldn't he be here? Tomorrow, gives us resistance. So that means with voltage and resistance, you've got all the electrical units that you need. And I think I'm going to skip a few slides and just say that in addition, we redefined the mole. Instead of the mole being the number of entities that are in 12 grams of carbon-12, it's just a number. We've just defined Avogadro's number. And the Kelvin, instead of being a fraction of the triple point of water, is now defined by defining the Boltzmann constant. So temperature, like kelvins, is defined in terms of the microscopic kinetic energy, the thermal kinetic energy of the constituents of the material whose temperature we want to know. These are beautifully quantum mechanical and microscopic definitions of these formerly macroscopic ideas. So what it means is that we now have a metric system that is realizing the dream of the French revolutionaries, which was to make a system of units that would be good for all time and for all people, except perhaps for time itself, because time is still tied to a specific atom, namely cesium, and we are soon going to need a new definition of the SI second based on not a microwave frequency, but an optical frequency standard, but it's still not going to be based on a fundamental constant. So people like Junyi, where is Jun? And is going to tell us a little bit more, I hope, about these things. And he and Anna Maria Ray, who's providing the theoretical muscle behind this, are measuring things to an accuracy of parts in 10 to the 18, but relative precision of parts in the 10 to the 21. So we're going to have a new definition of the SI second based on this. But what they're working on is to quantum entangle these atoms to beat the shot noise limit. So this is really 21st century quantum mechanics. So the definition of the SI second, I'm guessing, is going to change within a decade. Will it be the last change? Well, only time will tell. Thank you very much.